Yeah, welcome to our fourth Quantum BV colloquium. My name is Kara Stefan, and together with the co-chair João Bravo, we will guide you through today's colloquium. Yeah, last year, Quantum BV was kicked off as the state initiative for quantum activities in Baden-Württemberg to pool all these competencies and to create an overarching umbrella brand that further strengthens these networks and makes them more visible. And with this colloquium, we want to further promote scientific exchange on quantum hardware and algorithmic topics in the field of quantum computing to present the latest developments in this research area and to promote the idea of co-development in quantum solutions. Yeah, and today I have the pleasure of introducing our speaker, Professor Zoë Holmes from the École Polytechnique Fédérale de Lausanne. In 2015, Zoë Holmes received her MPhil degree in physics and philosophy from the University of Oxford. And in 2016, she obtained her Master of Research from the Imperial College London, where in 2019 she got her PhD in quantum thermodynamics. In 2020, she started as a postdoctoral researcher at Los Alamos National Laboratory, working on quantum algorithms and quantum machine learning methods for noisy intermediate-scale quantum computers. In 2021, she became the Mark Keck Fellow at Los Alamos National Lab, and since August 2022, she is tenure-track assistant professor at physics at the EPFL. Yeah, and today she will introduce us to the question, or maybe rather the answer to the question, whether provable absence of barren plateaus implies classical simulability. A large amount of effort has recently been put into understanding the barren plateau phenomenon, and in this talk, we face the increasingly loud elephant in the room and ask a question that has been hinted at by many, but not explicitly addressed. Can the structure that allows one to avoid barren plateaus also be leveraged to efficiently simulate the loss classically? So it presents strong evidence that commonly used models with provable absence of barren plateaus are also classically simulable, provided that one can collect some classical data from quantum devices during an initial data acquisition phase. And this follows from the observation that barren plateaus result from a curse of dimensionality, and that current approaches for solving them end up encoding the problem into some small classically simulable subspaces. This sheds a serious doubt on the non-classicality of the information processing capabilities of parametrized quantum circuits for barren plateau-free landscapes, and on the possibility of superpolynomial advantages from running them on quantum hardware. And then we end up discussing caveats in our arguments, the potential of smart initializations, and by highlighting new opportunities that our perspective raises. Yeah, you can post your questions in the chat. My colleague João Bravo, who is a PhD and the co-chair of this session, will collect them and guide the discussion later on. And with that being said, I hand over to you, Zoë.
Cool. Many thanks for the introduction. And yes, please do feel free to post questions in the chat as you go along. I'll happily have a bit of try and make this a bit more of a discussion. Because, well, as Chiara said, I'm going to answer this question. But it's not going to be a straightforward answer. I'm really asking this question: does provable absence of barren plateaus imply classical simulability? And really, the answer is a sort of a yine, a sort of yes and no, because it depends on your perspective. And one thing I want to stress is that this was a team effort, and many fun arguments were had in the making of this work. And it was impossible for all of us to completely agree, because some aspects of it, sort of roughly the first half of the talk, is just sort of cold hard facts, sort of the maths. But the second half, there's a lot of room open for interpretation. And I think we really don't know yet, no one knows yet exactly what conclusions we can draw from some of the things I'm going to say. Okay, so the focus of this talk today is hybrid variational quantum computing, by which, for the purpose of this talk, I mean any method that optimizes a parametrized quantum circuit by minimizing a cost function, potentially using training data. And this encapsulates variational quantum algorithms and many, but not all, quantum machine learning methods. So just in a little bit more detail, the idea here is that on your quantum computer, you are going to run a parametrized quantum circuit, and you are going to pick a faithful loss and parameterized quantum circuit such that once successfully minimized, successfully trained, either the optimal parameters, the optimal circuit, or the optimal cost function value is approximately a solution to your problem. By the way, I'm going to use the words loss and cost interchangeably in this talk, a mix of slides from different phases I've had at different points in time. Okay, so the idea is you have this parameterized quantum circuit. So that is some arrangement of gates with some parameterized gates. So these are typically parameterized rotations, so a rotation about some angle where that angle is a variable. You run your circuit with respect to a particular set of parameters. You then measure it at the end. This gives you your cost function value with respect to those parameters. You feed this cost function value to your classical computer. On your classical computer, you run your favorite optimization algorithm, Bayesian descent, gradient descent, sorry, Bayesian optimization, gradient descent, your favorite SciPy black box seems to do the trick in the optimizing, but if you're honest, you're not entirely sure what's going on under the hood. So anyway, you do on your classical computer, you do some form of optimization algorithm, and this tells you what parameters to try next. Then you feed those parameters to your quantum computer. You run your parameterized quantum circuit with these new parameters, and you just keep on minimizing, keep on looping around until you've minimized your cost. So this is a hybrid quantum classical optimization loop. And as I said, you want to try and pick your loss and pick your circuit such that once successfully trained, the optimal parameters, circuit, or cost are an approximate solution to your problem. Okay, so what follows, we're going to consider losses of this form. So you've got some initial state, you've got some parameterized circuit, and then you've got some observable that you're measuring, or could be a P of M element more generally. And this is because you have this flexibility of encoding all sorts of different optimization problems into your algorithm by picking different losses and different parameterized quantum circuits. It is an incredibly flexible paradigm that has been explored by many, many different communities over the last, I guess sort of 6-7 years now, with people trying to use it for machine learning, people trying to use it for combinatorial optimization problems, sort of traveling salesman type things, people applying it to mathematical applications, things like factoring, as well as a whole host of scientific applications, which are probably the ones I'm personally most interested in, things like finding ground states for different materials, or quantum chemistry, or dynamical simulation. Okay, but despite its popularity and its flexibility, people soon found that actually training these algorithms was hard. So it's all very well coming up with a loss and coming up with an algorithm. If you can't actually minimize your loss, then it's not very helpful. Now, there are many ingredients to trying to get trainability to work. So firstly, the expressibility of your ansatz, of your parameterized quantum circuit. So roughly how likely it is that your parameterized quantum circuit, your parameterized unitary, contains a solution. Secondly, loss gradients or loss differences. So this is basically how featured your landscape is, and so how easy it is to find a cost minimizing direction. And then we have the problem with local minima. So how much your landscape contains poor local minima that is easily to become trapped in, stopping the optimization. So lots of different ingredients to trainability. The one I'm going to focus on in this talk, and actually most of the literature has focused on, is on the question of whether or not we have loss gradients, or equivalently loss differences, substantial changes across your landscape. Okay, and the point here is that your loss landscape needs to be sufficiently featured to enable training. So compare these two different landscapes and imagine trying to find the minimum of these two landscapes using gradient descent. So finding the minimum of this point is relatively straightforward. You keep on following the steepest route down at any moment in time. So this sort of little man here is just going to end up following the stream down to the valley. But now imagine there is actually a very sort of golf ball style size hole somewhere in here, but no flag to mark it out. And you're trying to figure out where that little hole, the minimum of this field is. Well, it's almost entirely flat. And so trying to navigate there is effectively going to be a random walk. And note, this is particularly an issue in the context of trying to minimize a quantum loss. So if we have small gradients, or equivalently small loss differences, then you're going to need high precision measurements to figure out which direction minimizes the loss. You're going to have to measure very precisely to figure out whether this way is lower or that way is lower. Now, high precision measurements on a quantum computer, crucially, are really resource intensive. So a quantum loss is only ever measured statistically. So specifically 1 over sigma squared shots, so that is runs of the quantum circuit and then measurements, are required to estimate a loss to precision sigma. So if you need high precision measurements of small gradients, then you're going to need lots and lots of shots. Okay, so why is this a problem? This is a problem because there is something known as the barren plateau phenomena. So the barren plateau phenomena is when you can show that the variance in the partial derivative of a cost scales exponentially with the size of the problem. So n here is the number of qubits that the parametrized quantum circuit acts on. And if you combine this with Chebyshev's inequality, what you get is the probability of observing non-negligible gradients vanishes exponentially with problem size. So for small scale problems, the type that you can run on your laptop, the type that you can sort of easily run cheaply on available hardware, you might have substantial gradients. You may have substantial variation across your lost landscape and be able to train. But as your problem gets bigger and bigger, as you get to the type of sizes that we're interested in for quantum advantage, then your landscape is going to become flatter and flatter. And this means the number of shots required for training is going to grow exponentially with problem size. So you might be able to get away with some quite imprecise measurements and few shots for small scale problems, but for larger problems, the number of shots you need, the number of runs of your circuit in order to get high precision measurements to evaluate the cost minimizing direction is just going to blow up exponentially. Note here, barren plateaus were originally framed in terms of the variance of the partial derivative of the cost, so in terms of cost gradients. You can also frame it directly just in terms of the variance of the cost. So in this case, what we see is that if the variance of the cost vanishes exponentially, then the probability that the cost deviates from a fixed point vanishes exponentially with problem size. So it's sort of the height of this lawn is the fixed point. The deviations away from the sort of the average height are exponentially small. Okay, so the barren plateaus were first sort of discovered, realized, highlighted in this paper by Jared McLean back in 2018 now. So remember, a barren plateau is when the variance of the partial derivative of the cost, or just the variance of the cost, vanishes exponentially. And now over the last 5-6 years, there has been ongoing efforts by the community to identify the different causes of barren plateaus. So I'm about to go through these different causes pretty quickly. Don't worry if it's too quick, because I'm then going to tie them together in a sort of simpler unifying story in a few slides' time. Okay, so this was the original paper by Jared McLean. We then followed it up showing that if your circuit is too expressive, your parametrized quantum circuit explores too much of the solution space, then you're going to have a barren plateau. There was this nice paper by Carlos, Marie, and Nathan, which showed that if your parametrized quantum circuit generates too much entanglement, that can lead to barren plateaus. We had this paper where we showed that even if you have a nice circuit, an inappropriate choice in target learning problem, basically tackling problems that are too unstructured, that leads to barren plateaus. This seminal paper by Marco and collaborators at Lanel showed that an inappropriate choice in cost function led to a barren plateau. So specifically, if you use a global cost and have a random unstructured circuit, then you have a barren plateau. But if you have a local cost, whether or not you have a barren plateau depends on other factors like how expressive or deep your circuit is or how entangling it is. And finally, there was this paper by Samson Wang et al., where they showed that hardware noise flattens out the lost landscape, making it harder to train. Okay, so lots of ongoing research trying to pin down the cause of the barren plateaus. These were more recently tied together in a story. These two papers that, amusingly, in the way sometimes happens in science, came out at more or less exactly the same time. So these were independent projects. The other authors didn't know that the other people were working on it, and they came out within 2 days of each other. So these two nice papers here tie together some of those causes on the previous slide in terms of story, in terms of dynamical Lie algebra and group theory. Okay. So in parallel to this ongoing research trying to identify the cause of the barren plateaus, there has also been a whole series of ongoing research that's trying to be more positive, and proving that certain architectures and methods can provably avoid barren plateaus. So by provably avoid barren plateaus here, what we mean is that you can show that the variance in the partial derivative of the cost, or just the variance of the cost, vanishes at worst polynomially in system size. Note that this isn't great. Polynomially vanishing gradients could still be painful, because polynomials can still be painful. but it at least means that the number of shots you need only grows polynomially, and that seems less scary than exponentially. Okay, so the first architecture that people proved were bound plateau-free were what are known as shallow hardware efficient ansatzer with local costs. So this is kind of the positive side of this paper by Marco that I highlighted on the last slide. So what they showed is that if you have local loss, so you're only measuring a constant number of qubits, so the number of qubits you measure doesn't scale with the size of the system, and then you have a random brickwork circuit, but it's relatively shallow, so at most log depth, then you can prove that your variance in the partial derivative of the cost scales at worst polynomially. Then there's something called quantum convolutional neural networks. If you don't know what these are, don't worry about it. If you do, the thing to note is that these were also proven to be bound plateau free. And again, it's roughly that they are shorter depth circuits, and that's sort of the essence of the proof. Then there are certain symmetrized ansatzer. So the Hamiltonian variational ansatzer, if you have cleverly chosen generators or permutationally equivariant quantum neural networks, where you've got lots of correlations in your circuit. In these cases, you can use the results from these two papers I highlighted before, where you can use sort of group theoretic ideas to show that these are bound plateau free. And finally, small angle initializations. So you can have a deep circuit, but if you initialize all of your angles close to zero, you do a sort of Gaussian initialization around zero, or just uniform in some range from minus r pi to r pi, then these can also have variances that are worth polynomially vanishing. Okay, so again, that was a lot of references in a very short time. That's because historically this field grew via piecewise analysis. I'm now going to try and tie together all of these works in a much simplified story. Okay, so now we're going to slow down and do some sort of very simple maths. So the thing I want to highlight is that the loss function, the one I showed you before, so just initial state evolved under some parameterized unitary, measure some observable, is effectively an inner product, a similarity measure. So that is, you can view it as an inner product between the Schrödinger evolved state and an observable, or you can see it as the inner product between the initial state and the Heisenberg backpropagated observable, where I'm just talking about the Hilbert-Schmidt inner product. Now, this should immediately raise red flags because we're looking at the inner product between two objects that live in an exponentially large space. And if you're looking at the inner product between two objects in an exponentially large space, typically the inner product will be close to zero. So that is, it's going to be exponentially small and concentrated with high probability exponentially close to zero. And this really is the first claim, that bound plateaus all boil down to the fact that we are looking at the similarity between objects that live in an exponentially large space. And so as the space grows exponentially, their overlap is going to become closer and closer to zero. The two objects are going to become further and further apart. And so the loss function will become exponentially concentrated. So that is, the claim is that bound plateaus at their core arise from the cursor dimensionality. Okay, so let's pin this down a bit more. The question we want to ask now is, when does this cursor dimensionality kick in? So remember, we're going to have a loss of this form, and I'm going to focus on the version where we think of it as an inner product between the state and the Heisenberg backpropagated observable. So we have this observable. We could, if we want, write it as a sum of some other terms, so sum of C lambda, P lambda. These P lambdas are any basis you fancy, but probably it's easiest to think of it as a Pauli basis. And what we want to ask is, when does this Heisenberg backpropagated observable explore an exponentially large space? Okay, and I'm just going to first address this question a little bit pictorially. So let's imagine that we have one term here, some P lambda term that is global. So that is, we have measurements on all qubits. Now, if we have measurements on all qubits, and we just have a very short depth circuit, so even just a single layer of single qubit rotations, you can turn one global Pauli onto any of the other global Paulis just by single qubit rotations. so a very short depth circuit. So that is, you can transform one global Pauli to all the other global Paulis, and there are exponentially many global Paulis. So that is, if you start with a global measurement, even a very short depth circuit, you can explore an exponentially large space. On the other hand, if you have a local observable, so let's say we're just measuring a single Pauli here and a shallow circuit, then you have a light cone effect. So this local Pauli, after one layer, well, it's still pretty local. After two layers, it's 2 local. After 3 layers, it's 3 local. So its locality is bounded. So you only have, you can only create basically local Paulis, somewhat local Paulis, and there's only going to be a polynomial number of local Paulis. So that is, if you have a local measurement and a shallow circuit, you're stuck exploring a polynomial space. On the other hand, if you have a local Pauli and then a deep circuit, so these lines here are meant to denote that the circuit's going back deeper, I just haven't drawn it, then soon your light cone will reach the edge of the circuit, and you're going to again be exploring all n different global Paulis. Well, so it's going to be a Pauli on each of the n qubits. So you're again going to be able to create all of the global Paulis, and there are exponentially many global Paulis. So that is, if you have a local measurement, but a deep circuit, you are exploring an exponentially large space. So what we see here is that both the circuit depth and structure in part determines where we go, but also the choice in the initial measurement determines where we can go. So global measurement, short or long depth, exponentially large space, local measurement, shallow depth, polynomial space, deep depth, exponential space. And so if we tie this in with the story I said before, where we said that barren plateaus arise from comparing objects that live in an exponentially large space, what we see is that if we have global measurements, we're always going to be in an exponentially large space and have barren plateaus, at least for random circuits. If we have local measurements, if we have deep circuits, deep unstructured circuits, then we're going to be exploring an exponentially large space and have barren plateaus. But if we have local measurements and shallow circuits, then we can be in a polynomial space. So what we see is that this is basically a really quick pictorial explanation of the results in the cost function dependent barren plateau paper, where he argued that for global costs, you have barren plateau, and for local ones, it depends on the depth of your circuit. Okay, so that was a pictorial explanation. We're going to go back to a bit more maths now. So as I said, we're going to look at the loss as an inner product between the Heisenberg backpropagated observable and the initial state. And we're going to take the observable to be some of, let's say, Paulis. And now what we're going to do is we're going to look at the Heisenberg backpropagated operator for each of these terms in this sum. So these p lambdas of thetas. So this is p lambda of theta is just u of theta times p lambda u dagger of theta. And then we're just going to define b lambda as the subspace in which these p lambda of theta operators live. Okay, so let's now see how we can use these kind of definitions to rewrite the loss. So we have the loss here as, well, the loss is just initially just the inner product between rho and O. And then I'm just going to substitute in this definition of O. And what you see is that the loss is now the sum of these backpropagated terms, the inner product between the backpropagated p lambda term and rho. Okay, and then the key thing to note is that we're now looking at the inner product between rho and p lambda of theta. And now we've just said that the p lambda of theta lives in some subspace that we're going to call b lambda. So what we can do is actually simplify this expression and just project the initial state rho down onto the subspace b lambda. So we're just going to say rho on the subspace b lambda is just going to be this thing we call rho lambda. And so what we see is that the loss can be expressed as a sum of inner products in each subspace. So that is an inner product between the backpropagated version of each of the terms in the observable and the initial state projected down onto the subspace into which that backpropagated term lives. Okay, now, if any of these subspaces is only polynomially large, so polynomially large rather than exponentially large, then the overlap between the projected state and the backpropagated term, or equivalent the loss, can also only be polynomially concentrated. So we no longer have this cursor dimensionality because we're now comparing objects in a polynomially large space rather than an exponentially large space. Note that the initial state here is really important. So if the initial state is too entangled, then when we do this projection down onto the subspace, so when we transform our row to our row lambdas by projecting down into the subspace B lambda, if our initial state is too entangled, then it's going to be close to maximally mixed. And then if you're looking at the inner product basically between identity and some observable, well, let's assume these are just Pauli's, that's just trivially going to be 0. Or equivalently, you're basically getting no information out. If you're just looking at, if your reduced state is close to maximally mixed, everything becomes trivial. So not only do we need these subspaces to be smaller, so sort of polynomially large rather than exponentially large, we also need our initial state to not be too entangled. So more concretely, you can frame this in terms of sort of volume law or area laws of entanglement, if you're aware of those, by which I mean, by volume law, I mean that the distance between our state and the maximally mixed state is, so volume law would be the distance between your initial state projected down and the maximally mixed state is exponentially small. Volume law means that there's at least a polynomial difference between your initial state and the maximally mixed state. If you're not familiar with the volume law and area law definitions, no stress, that's not so important. The key idea is that your initial state must not be too entangled, because if it's too entangled, when you trace stuff out, look at the reduced state and look at row lambda, you're going to get something that is close to maximally mixed and so contains no interesting information. And note, this is effectively a reinterpretation of the entanglement-induced barren plateau paper, because we've again sort of rediscovered from this perspective that the initial state can't be too entangled. Okay, so that was a sort of the big picture story. And that takes us to sort of claim one that I want to make that is sort of concrete for the day. And that is the fact that provably barren plateau-free architectures live in classically identifiable polynomial subspaces. So that is all of those references I showed on previous slides for different cases that people had proven could avoid barren plateaus. So shallow hardware efficient ansatz, quantum convolutional network, small angle initializations. These ones here that have slightly technical sounding names, these are basically ones that use symmetries in clever ways. So all of these cases that people have proven can avoid barren plateaus. If we look under the hood, we can see that the way in which they avoid barren plateaus is by basically encoding the problem into a classically identifiable polynomial subspace. So I appreciate there's a lot on this table. I don't expect you to take it all in. But the point is, if you want to, you can sort of dive into the literature, dive into our paper and see how in each of these cases there is a corresponding polynomial subspace. One thing I want to highlight here is that actually it was the very proof of the absence of barren plateaus that allowed us to find these polynomial subspaces. I'm going to come back to this point later. It could be that certain architectures don't have barren plateaus. We don't know how to prove this. And then we can't identify the polynomial subspace. Okay, so this is where sort of the phantom of classical simulability comes in. So if these provably barren plateau-free architectures live in classically identifiable polynomial subspaces, well, wasn't sort of the exponential size of Hilbert space meant to be the thing that gave quantum computing its power somewhat, that certainly made quantum circuits hard to simulate a lot of the time? If these architectures that we can prove avoid barren plateaus do so just by encoding the problem in a polynomial subspace, well, doesn't that mean that we can maybe classically simulate it? So I'm going to come onto that point in a second, but before I do, I just want to pin down the notions. I'm going to pin down a notion of classical simulability that we're going to discuss. So we're going to have this class called CSIM, which is when everything is fully classically simulable. So CSIM is when you run a simulation of your VQA on your laptop, when everything is just done classically. So that class, I think everyone's pretty familiar with. Now, QSIM is what we call sort of the standard VQA setting. So standard VQA setting, where you do this hybrid quantum classical optimization loop, you run your circuit with a certain set of parameters. That gives you your cost. You feed this to your classical computer tells you what parameters to try next, etc., etc., and you keep on looping around. So that's QSIM, sort of the standard VQA setting. And then we're also going to talk about this slightly more subtle in-between class, which we call CSIM-QE. So this is quantum enhanced classical simulation. We weren't sure what to call it. It's somewhere in between the two. And the core idea here is that you can use your quantum computer initially to gather some data, do some kind of tomography, classical shadows. It will vary from context to context. And then you pass the classical data you get out of running those quantum experiments to your classical computer. And then your classical computer runs an algorithm after that. So key difference between QSIM and CSIM-QE is that in CSIM-QE, you don't adaptively and interactively run stuff on the quantum computer and then classical. You have this kind of limited use of the quantum computer at the start. Okay, so just to make some things clear, a quantum advantage is possible for any problem where you have to use a quantum computer. So that is for any problem which is in either CSIM-QE or QSIM, but not CSIM. Because in both cases, you do use the quantum computer at some point. But you only need to actually run the VQA sort of in the standard format of running your circuit on the quantum computer, passing your cost function value to your classical computer, looping around, etc., etc. You only need to do that in QSIM. You don't need to do that in CSIM-QE. So that is, you only have an advantage from actually running the parametrized quantum circuit on the quantum computer for problems that are in QSIM, but not CSIM-QE. Okay, so having set out those definitions, let me go back to the question about the phantom of classical simulability. So I was saying that if we did a case-by-case analysis, we saw that all provably bound plateau-free architectures live in classically identifiable polynomial subspaces. And then the question was, well, does that mean we can classically simulate them? And I think the fact that the parameterized quantum circuit can be classically simulated is actually relatively clear just from looking at the different cases. And actually, this was increasingly discussed. There's nothing really new here, but arguably hadn't fully sunk in all corners before we put our paper out, and arguably still hasn't in some corners. So the actual circuit, basically these log depth shallow random circuits, or something like a quantum convolutional neural network that's also relatively shallow, or some of these highly symmetrized circuits. In all of these cases, the parameterized quantum circuit, the U of theta, can be classically simulated. And so this means that the loss can be classically simulated for classical initial states and measurements. So just to pin this down a bit more, all of these cases where you're basically working with low entangling circuits, so this includes the shallow hardware efficient ansatz, this brickwork thing, or the small angle initializations, all of these can be simulated via tensor networks, or light cone methods, or potentially some of these sort of Clifford plus tree methods. And then all of these circuits that use symmetries in clever ways, these can be simulated via well-known algorithms for simulating symmetrized quantum circuits. So these are sort of group theoretic ideas. So in all of these cases, the parameterized quantum circuit can be classically simulated, and so the loss can be classically simulated for classical initial states and measurements. But I used to say, for non-classically simulable initial states and measurements, then we'd need to run the VQA on the quantum computer. Because it didn't matter if we could classically simulate the parameterized quantum circuit, if the quantum circuit itself, if the initial states, if the measurements weren't things we could simulate classically, then we were screwed and we needed to do the rest on quantum hardware. And that was cool. Then we actually needed to use the quantum computer for something. But we've just seen that in all of these cases of provably bound plateau-free architectures, that they live in classically identifiable polynomial subspaces. So if the Heisenberg observable lives in a polynomial subspace, even when we backpropagate it, then all we need to do is project the initial state down onto that subspace. We need to basically get a classical representation of it by some kind of tomographic procedure, and then we can simulate the rest of the VQA classically. Okay, so let me just pin this down a bit more mathematically. So remember from a couple of slides back, we did this trick. So we started with the loss, and we showed that it could be written as the sum of the inner product between the initial state projected down onto some subspace B lambda and each of the Pauli terms back propagated that lived in that subspace. So it's an inner product between the back propagated version of each of the terms in the observable and the initial state in the subspace corresponding to where that observable lives. So the loss is the sum of inner products in each subspace. So that means to simulate this loss, all we need to do is compute a basis for each of these B lambdas and then project the initial state onto that basis. So if we have a classical representation of the initial state, we can have a classical representation of this projected state, these rho lambdas, and then we can do the whole problem classically, the whole simulation classically, and the problem's in CSIM. If we do not have a classical representation of the initial state, then we can do this on a quantum computer. So all we need to do is some form of tomographic procedure in order to compute these rho lambda terms. And then once we've got that, we can do everything else classically. And crucially, for provably bound plateau-free architectures, they live in polynomial subspaces. So that is, these B lambdas are polynomial subspaces. So that means projecting rho down onto the subspace and getting these rho lambdas is only going to take a polynomial number of measurements. So that means the problem is in CSIM-QE, is in this quantum-assisted classical simulation, because we can run the whole algorithm just with a polynomial amount of resources from the quantum computer initially, and then simulating everything else classically. Okay. So just for a concrete example, for the shallow hardware efficient ansatz we discussed earlier with the local loss, what we saw is that if you've got a local loss, then the back propagated term is going to be somewhat local. So that means the subspace B lambda are just these sort of local subspaces. And so all we need to do in order to basically project the initial state rho down onto this subspace is just measure polynomially many Paulis acting on log n adjacent qubits. So basically you do reduced state tomography on this subspace. And once we got that, we will have our rho lambda, and then we can simulate the evolution using reduced light cone methods. Okay, so time for another big table. The claim is, claim 2, all problems in polynomial subspaces are classically simulable after potentially a tomographic procedure where we project the initial state down onto the polynomial subspace. So again, we can look at all the different cases that people have proven avoid barren plateaus, and we can identify the tomographic procedure that might be needed if rho is quantum in order to project it down onto a subspace. We can then identify the simulation algorithm, and then we also provide guarantees about whether it's simulable for all theta or just on average with high probability. Okay, so the punchline is, if we combine claim 1 with claim 2, we know that all provably bound plateau-free architectures live in polynomial subspaces, and all problems in polynomial subspaces are classically simulable, potentially after getting data from a quantum computer. And so what we see is that in none of the standard problem instances with provable absent of bound plateaus does the parametrized quantum circuit need to actually be implemented on a quantum computer in order to estimate the loss in polynomial time. Okay. And note, this actually has a flavor of this old paper by Robert Huang. So Robert Huang now, I think sort of 4 or 5 years ago, put out this paper on the power of data in quantum machine learning, where he shows that actually a very powerful learning paradigm is to first get data, classical data from quantum experiments, and then do the rest of the machine learning classically. And what we're claiming now has a very similar flavor, that you don't necessarily need to run this VQA adaptively, interactively. You can just get some data off your quantum computer and then do everything else classically. Okay, so where does this leave us? So this is the transition from the sort of the cold hard facts to how can we interpret this. And so the remaining of this talk is I'm going to discuss sort of some caveats and opportunities in this argument. So first big caveat is that the quantum computer, well, can still be crucial. So In any case where the problem is in this quantum enhanced classical simulation family rather than just the classical simulation family, then the quantum computer is still very much needed to collect data. It's just used differently. It's used non-adaptively to basically create some kind of surrogate, which is then used for training. Note that there's the caveat here that this is only when the initial state or measurement is quantum. So problems like quantum machine learning with classical data, it's harder to construct examples where actually the initial state is really something that is non-classically simulable. But for inherently quantum problems, sort of more scientific problems, it's relatively easy to construct examples along those lines. The other caveat along these lines is that sort of the advantages or disadvantages between surrogating, so this kind of CSIM-QE, this quantum enhanced classical simulation approach, versus just the standard VQA approach, can become blurred at times. So we're comparing polys and polys. We're saying that the VQA is always going to only ever run in polynomial time. And this CSIM-QE, you're going to need a polynomial amount of data from your quantum computer initially, and then run everything else classically. So it might be that actually one of these methods is polynomially more efficient than the other. This is still something that needs to be investigated. And I think I will not discuss this more right now, but I'm really happy to answer more questions on this because I have some intuition about cases which I think it will be better to run the VQA, and certain cases where I think it'd be better to do the CSIM-QE style, just get your data, then do everything classically. Okay, second thing is our argument is a case-by-case argument. It is not an absolute argument. And indeed, if you try hard, you can construct counterexamples of non-concentrated losses that are not classically simulable based on basically cryptographic assumptions. So it's just, if you've seen these papers, there's lots of papers along these lines. You can basically smuggle Shor's algorithm in order to create a counterexample and show that you have to use a quantum computer. In our case, you also have to use it non-adaptively. That said, I would have to stress that the counterexamples that we've managed to create are weird. They're really weird and contrived. They do not resemble what most people are actually doing on VQAs. Not even most, anyone's really doing in VQAs. So I don't think they are a useful, interesting counterexample in terms of actually something someone would want to do. However, they can maybe give us insights in how you can create more interesting counterexamples. And that is basically what this counterexample does is it breaks the assumption that comparing objects in exponentially large spaces typically leads to concentrated expectation values because it uses heavily structured circuits. So I said at the start that we're looking at it in a product between two objects that live in an exponentially large space. Typically, this overlap will be exponentially small. But the word typically is doing a lot of work there. If you pick your objects well, they can be nicely aligned, and then the overlap is not exponentially small. And this is effectively what conventional sort of fault tolerance style algorithms do. They can use cleverly designed circuits so that your expectation values are not exponentially vanishing. So I think the insight here is that maybe we can try and draw more inspiration from sort of conventional fault tolerant algorithms to come up with new variational quantum algorithms. Third small caveat, our argument applies to losses of this form. Some forms of VQAs do not fit in this framework. I think most do. They either look like this or they're something like sums of terms of this or some classical processing of terms that look like this. But there are some things, e.g. Boltzmann machines, that don't fit so well in this framework. And again, maybe this points to trying to be a bit more imaginative and come up with more losses, more sort of fault-tolerant inspired variational quantum algorithms, other learning paradigms that don't look like this. Okay. And now this is probably the most important caveat. So that is both bound plateaus and in places our notion of simulability, our average case notions. So a bound plateau can have substantial gradients in exponentially small subregions. So we say that a bound plateau is a landscape which with high probability is flat almost everywhere. So with exponentially high probability is flat almost everywhere. But that still leaves wiggle room for some small regions where we have gradients. And also in some cases, our notion of simulability is an average case notion. And so simulation might also not be possible in certain exponentially small subregions. I might actually skip out these technical details, but if they come up in questions, I will go over them. The point I want to highlight is that you can draw a distinction between an average case notion of simulability and a worst case notion of simulability. And you can also actually, when I'm talking about these polynomial subspaces, we can draw a distinction between sort of absolute polynomial subspaces and effective ones, where the absolute ones, it happens for all theta, and it's sort of, there is no small tails outside of the subspace, whereas these effective subspaces, you have these small tails and you're only in that subspace with high probability. And so actually back in this big table, if you were really eagle-eyed, you'd notice these P's and E's, and this is us telling you whether or not you're in a strictly proper subspace or just an effective one. And then this distinction carries over to our simulability table, because it's the ones that are in proper subspaces that we can simulate for all theta, whereas the ones in effective subspaces, so these are the quantum convolutional neural networks and small angle initializations, you're only in an effective subspace, and this means that we can't have guarantees that you can simulate for all theta, but rather for theta with high probability. So I skipped over that quite quickly. The thing I just want to highlight here is that in certain cases, namely quantum convolutional neural network and small angle initializations, there's a bit more wiggle room. Our results are not so strong because you can't necessarily strictly simulate for all theta. Okay, but the main idea here is barren plateaus and our notions of simulability are average case notions. So it could be that there is potential offered by warm starts where you try and initialize cleverly in these small, exponentially small regions that actually have gradients. And I think an important caveat here is that we need these substantial gradients, not just around the initializations, but also along a nice trajectory from where you initialize to where you're trying to get to. And then the question is, if the gradients are exponentially, with probability exponentially close to 1, vanishing over the whole landscape, how likely is this? So if you manage to find some gradients at your initialization, you also know you have to have gradients close to the solution. If we know that on a barren plateau, the probability of finding gradients is exponentially small, what's the probability that you're going to have a nice trajectory linking the two? And I'd really say that most disagreements in the community now about the barrier posed by barren plateaus boil down to this question. So there are those of us who look at the maths and just think this seems unlikely. And then there are those people that come maybe from a more heuristic classical machine learning background who say that optimization often just works way better than you expect, that then sort of keep some optimism and still think that we might be able to find these special trajectories. And actually, I just want to throw out that in this recent paper with my 2 students, Rickard and Mark, we start trying to explore some of the analytics around warm starts and the potential that they might or might not offer. Okay, so opportunity here is I think there's a lot of wiggle room to investigate clever warm start strategies. And I think I will highlight that among the team, there are many disagreements about how much potential warm starts offer. Okay, and now this takes me to my final point. Everything we say relies on proofs of absence of barren plateaus. But it might be possible that we can heuristically find gradients, but no identifiable poly subspace. And because we can't identify the polynomial subspace, we can't simulate. And some people like to point out that maybe this is analogous to the classical case. So classically, optimization, as I was saying, works so much better than you would expect. Way more than we can prove or explain. Right now, theorists in classical machine learning are trying to understand why classical machine learning is so successful. That said, I think it's important to remember that precision is much more expensive quantumly than it is classically. So classically, you want to double your precision, just add another digit. Quantumly, you have to have someone in a lab run the experiment for double the amount of times. Which means that if you have flat landscapes, it's much harder to get that extra precision you need to navigate. So that's the first point. Second point is also the fact that classical machine learning is so successful means we have a high bar to beat, particularly when you're picking between running your standard VQA versus doing your data acquisition and then running everything classically. Because in this sort of CSIM QE setting, this quantum enhanced classical simulation, once you have all your data, you can throw your favorite tools from classical machine learning at it, which maybe makes your life easier. So how strong the analogy is with a classical case, I think, is anyone's guess. I think there is reason to look towards it and see whether we can learn from it. But there might also right now be an element of blind faith that people are just kind of praying to the gods of classical machine learning and hoping that it will work out as well as it did classically. Okay, and with that, I will go back to the raw facts. The raw facts are that barren plateaus are a curse of dimensionality, that provably barren plateau-free architectures live in classically identifiable polynomial subspaces, and problems in known polynomial subspaces are classically simulable, or classically simulable after potentially getting data from a quantum computer. And how to interpret this, I think, there's lots of room for discussion, and this is cool because there's sort of lots of future opportunities to investigate. Okay, thanks for listening.
Thanks a lot, Zoe, for this really great talk. I think it was a really good add-on to the paper for anyone that has already read it or is interested in reading it. So my computer kind of has some technical issues, so I'm coming in from my phone.
Wow.
But I guess there is, let me look at the questions. Okay, there is one question from the audience about the role of the operator. So does the unitarity of the quantum operators, does it play a role in the barren plateau problems? And would relaxing the condition of operators to be non-unitary be helpful?
No, I think it just makes it worse. Think about Steinspring dilation. So you can just think of any channel as a unitary on a larger space, and then you've just encoded the problem in an even bigger space. So you just have an even larger exponential to contend with. So I think certainly generically, relaxing the unitarity makes it worse. Maybe there are some clever, okay, fine. So there's this, and I should actually update my slides for this. There's this paper on the role of non-unital noise. And you see that if you add non-unital noise, you can provably avoid barren plateaus. So non-unital noise, just think of it as amplitude damping. So you have some probability to end up in the all-zero state. That helps you avoid barren plateaus, but it basically does it just by restarting the circuit. So if you have some probability to drop down to the zero state at some point within your circuit, it's almost like you just shorten your circuit, you're just starting again. So this paper that shows that non-unital noise can help avoid barren plateaus, in parallel, they also show that you can simulate these circuits with non-unital noise because you live in a polynomial subspace. So it was actually a nice example of a paper that came out after our review, but they took insights from it in order to understand their results.
Yeah, that makes sense. Let me look at other questions. Okay, there's another one. So Roberto is asking, how does this discussion extend to quantum kernels? And are there strategies to avoid exponential concentration in kernels? And
okay,
if those are also classically simulatable?
Okay, so I have a paper on exponential concentration in quantum kernels. When we look at the causes of exponential concentration in barren plateaus, and causes of exponential concentration for kernels, the causes are pretty similar. So again, too much expressivity, too much entanglement, global measurements, all of that side of things. I have an echo. Better. Okay. So the causes are similar. The manifestation is slightly different. Because kernels are convex, even if you have exponential concentration, you can still train on your training data. It's a convex problem, you can always optimize. But what you find is that what you optimize, because you have exponential concentration, you basically have the same kernel values independent of what your training data is. So what happens is you basically cook the solutions. So say you've got a classification problem or regression problem, you manage because you've got this convex problem, you basically cook your solution so that it perfectly fits on your training data. But because your kernel values are completely independent of your training data, your predictions on unseen data are the same no matter what your training data is. So it's kind of cute that you end up with a different problem. You can train when you have exponential concentration in kernels, but really it leads to poor generalization or trivial generalization rather than a training problem. And it's a really funky type of generalization problem, actually, because it's a type of generalization problem that's improved not by using more training data, but actually using more shots. So yeah, we've got a paper on this called something like exponential concentration and kernel methods, if you're interested in learning more, where we pin down the causes of exponential concentration and the effect. We don't discuss classical simulability in that paper. I think there is a very similar story to be told, however. But it's more subtle because basically kernel methods are kind of already in this CSIM-QE setting. So they're already non-adaptive. And actually, I think the more interesting story to be told in the context of kernels and classical simulability and exponential concentration concerns some of these new methods on random Fourier feature surrogating. So people are saying that these kernels are often surrogatable. And I think there's some nice links potentially there between whether they're surrogatable versus whether they concentrate and whether or not there's wiggle in between the two. But again, for kernel methods, we have the discrete logarithm problem can be solved via kernels. So we know that they're not sort of completely dequantizable. This was this famous IBM paper with Christian Temer and a bunch of others.
Mm-hmm. Yeah, thanks. Maybe there's a bit more time, so I'll ask a question too. You mentioned this potential of special initializations. Could you briefly discuss how these might help avoiding barren plateaus without leading to classical simulability, and how to actually implement this in practice?
Okay, so the core idea here is that obviously close to a minimum, you have to have gradients. Mm-hmm. We know that. And then the question is, well, and so then what we do in this paper, and we've got some follow-ups on this coming, is you want to explore how large is that region close to a good minimum. So how close to that minimum do you need to initialize in order to have good gradients? And what we can prove is basically lower bounds on the variance within this region. So we say that if you are in a region that is of basically radius 1 over square root m, where m is the number of trainable parameters. So instead of looking at the variance over the full landscape, so for each of the parameters between 0 and 2 pi, you look at the variance in some region, which is basically the minimum plus or minus r pi, where r is a small fraction of 1. So r is 1 over square root m, or scales as 1 over square root m, where m is the number of trainable parameters. Then we can guarantee variances that vanish at worst polynomially. And then the big question is, well, how the hell are you going to initialize so close to a minimum? And I think that's a really important question in all areas. In this paper here, we explore one approach that you might use to do that. So this has been proposed by a bunch of people. And the idea is, it's almost not like a warm start, but like a continual warming. So this is an algorithm for both real and imaginary time evolution, which is iterative. So what you're doing is you take an initial state, you evolve it a little bit further in time, and then you try and variationally learn a circuit that is shorter depth than the trotter evolution circuit. Once you have that, what you do is you evolve with that and another little trotter step, and you then try and variationally learn a compressed version of that sort of 2-time trotter step. And you just keep on iterating this forwards. And the idea, if your initial trotterization you're trying to learn is short enough in time, then basically just initializing at identity, and you're going to be quite close to the solution. Basically, if the thing you're trying to learn is close enough to identity, your time step is short enough, you should basically start within this narrow gauge. And if you then learn well, at the next time step, you're just trying to learn the difference between 1 time step and 2 time steps. So if that time step is short enough, again, you should stay within this narrow gorge, this dip around the minimum, you should have gradients and you should be able to learn. And so we provide bounds on, in what region you're going to have gradients, how small that time step needs to be, things along those lines. So that's the intuition of warm starts. You basically want to somehow get close to a minimum. And then once you're close to a minimum, you will have gradients. One caveat I will add is we can also show that it is possible. So that's not in this paper, but it's in a follow-up that's coming, that this is not a counterexample to the claims in the perspective. So in these cases where we can prove lower bounds on the variance due to warm starts, we can also show that that the problems in CSIM-QE, that you can basically come up with a surrogate to simulate in that region non-adaptively. However, this is one of these cases where I think the advantage of just running the VQA versus doing the CSIM-QE type thing becomes blurred. Because we show that you can create a surrogate in this small region, but it's quite time consuming. Unlike some other cases where you're basically just measuring local Paulis, as in the sort of the shallow hardware efficient case, the surrogate that we can prove in this case actually just involves measuring the cost at different points. So just sampling the cost at different points around this minimum. And if you're going to do that, maybe you're better off just running the VQA. So I would say that warm starts of the form that we have investigated here are still consistent with our main claims in this paper, but they do highlight that maybe you don't always want to do this quantum assisted classical simulation. Maybe sometimes you just want to run the VQA. And final point I'd say is that we're still in like the land of trying to prove stuff here. We're still trying to prove that you have gradients. It might be that there are special initializations where you have gradients, but we can't prove it. So we can prove gradients because we're close to a minimum, and we can basically just show in some region around a minimum we have gradients. But you could have some really funky looking trajectory that's sort of this tiny, small, sort of little worm through the landscape that has gradients. This sort of, I don't know, we call them fertile valleys. Think of it as like some little weird shaped gorge. And trying to prove that you have that is going to be really hard, but you might just find it when optimizing. And I think in those cases, if you just find that you have those when optimizing, you're not going to be able to surrogate it, because you're just not going to be able to know where to sample in order to get that polynomial region and map it out.
Okay, that makes sense. Well, thanks a lot for answering all these questions and for the talk. Yeah, I think I'll pass my word to Chiara again.
Yeah, thank you, João. Actually, I just saw there is another question in the chat, and I think we just might take the time to answer this one as well. Pietro is asking, do you think research community is focusing too much in applying knowledge from classical information world instead of trying to exploit, discover useful mechanisms which are inherent to QM?
So that is perhaps true when you are thinking completely outside the box and trying to do quantum machine learning more generally. I think maybe we want to be trying to come up with really sort of inherently quantum machine learning paradigms. On the other hand, I've often heard the point made in the opposite direction. So this is kind of in line with this slide, that the quantum algorithms community is all about proving resource analyses. The quantum algorithms community is all about trying to prove that something is polynomial, not exponential, that it's efficient, blah, 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 blah. Whereas the classical machine learning community just does stuff and it works, and it doesn't worry about proving it. It has intuitions of why things are going to work better than others. It tries to use nice structures, and it doesn't worry about proving whether things are polynomial or exponential. So Maria Schold, for example, makes this point a lot. So I've heard that argument, and then I think the obvious pushback to that argument is, well, that's because stuff works classically. It's not clear that stuff is actually working quantumly right now. We don't really have the large-scale, good quality machine to just run stuff and try and show it works. And so it makes sense to try and prove scalability. because otherwise people are just suggesting things that aren't going to work, or we suspect aren't going to work. So yeah, I'd love people to really use imagination and try and come up with new inherently quantum methods, but there's not a huge amount out there that I've seen. But it's a nice thought.
Yeah, so I'd say challenge accepted.
Yeah.
Yeah, thank you so much, Zoe and Joao, for your insights and the discussion. And I will now promote the next colloquium, which is already happening in 2 weeks, and it's the last one before the summer break. And we will have Professor Jens Eisert from the Freie Universität Berlin on site presenting his work on another question. The question is whether quantum computers have applications in optimization and machine learning. So we already know a tendency here, I guess. So yeah, thank you for your attention and have a nice afternoon.
Cool. Thank you. See ya.
Thanks a lot.